Good morning. I welcome you all to this session of fluid mechanics. If you recall, in the last class, we mentioned about the class of problem that when a fluid body is moving with uniform velocity or with uniform acceleration, what will be the force field generated in the fluid body, which we will be discussing today. So, first of all, you must know that when fluid body is moving with uniform velocity, that is velocity is uniform throughout, the velocity field is no longer required to be found out because velocity is same. So, in that case, we can find out a pressure field from the velocity field by the application of Bernoulli's equation in case of an inviscid fluid. And in case of a viscous fluid also, since the velocities are uniform, there is no shear stress developed in the fluid because there is no velocity gradient, so shear stress cannot come into picture. So in either cases, the fluid will behave as an inviscid fluid, or you can tell it is an irrotational fluid, where pressure field is found straight from the Bernoulli's equation, that P by rho plus V square by 2 is constant in the flow field, of course with the elevation head. Then we can find out the constant with some reference boundary condition. This is a very simple class of problem with uniform velocity, simply a rigid body translation or a rigid body rotation. Now, if we consider a uniform translation, what is the case? That means if a fluid body is translated uniformly. This happens, for example, a fluid body contained in a tank, solid tank. In practice, the tank is accelerated in certain direction with a uniform acceleration. In some direction, it may be along the coordinate direction. So, in any direction, if the tank is accelerated uniformly, what will be the force field generated or the pressure field generated in the fluid body? So, this is the precise problem for today. So, let us now analyze this problem with uniform translation. Let us consider a axis like this. OX, OY, OZ with this coordinate axis. Let us consider a tank like this. Let us. Now, not tank, let us consider a fluid body. Let us consider a fluid body now, appropriate to the coordinate axis in a Cartesian coordinate system. Now, we take a general case that the fluid mass, that means this fluid mass which we have taken here, separate fluid mass, is accelerated in both x, y and z direction. These are the component of acceleration. That means it is accelerated in x direction by ax, accelerated in the y direction by ay, and accelerated in the z direction by az. These are the components of acceleration in x, y and z direction. Well, now let us define as usual. Dx is this dimension, dy is the dimension of the parallelepiped along the y direction, and let this is dz. That means dz is this one. This one is, let this one is dz. This one is dz. That means the parallelepiped of dimension dx, dy and dz. Now, how to find out the pressure field? So, simple thing is that the way we found out the force equilibrium condition, hydrostatic force equilibrium condition, it is the same way, only that is inertia force is acting because of the acceleration. It's extremely simple. If you define the pressure at the center, it is better, more generalized approach. I did earlier that P plus del P del. Rather, P is defined at the center uniquely for this parallelepiped. So then what is the force on this plane if we now again define to recognize the plane A, B, C, D, and this one is E, this one is F, this is G. I have not drawn this with dotted line. These are the back lines from, if you see from this. However, so the plane AFHD is the x plane and CGEB are the x planes. Now, what is the pressure in this x plane and what is the pressure in this x plane in this direction? Pressure in this x plane, which is separated from the center by a dx by 2 distance in the positive directions, will be P plus del P del x dx by 2, neglecting the higher order term. That means this is the increment of P due to a change in dx by 2 in the positive direction. Therefore, pressure here will be P minus, that is, this is also an increment of P from that to this plane for a change in x that is separated by a distance minus dx by 2. That means dx by 2 in the negative direction. That's why the negative sign is there mathematically. Similarly, for this y direction, there will be pressure forces for the y plane. That means for the y plane. That means the pressure forces in DCBA, similarly HGEF. For HGEF, this pressure forces, this force, that means this force, perpendicular to the face HGEF, which is at a distance dy by 2 from the center of this parallelepiped along the y direction. So therefore, this magnitude will be P plus, I think you follow it, del P del y into dy by 2. That means the pressure in this plane HGEF, that is the back plane, which is displaced from the point P along the y direction by dy by 2, because this is dy. So this is center point, so dy by 2 plus dy by 2. So it is increased. Similarly, the front plane, that DCBA or ABCD y plane, which is separated from P or displaced from P in the minus dy by 2, that means in the opposite direction of the positive y direction. So mathematically this will be P minus del P del y into dy by 2. Alright. Similarly, the pressure at these planes, this pressure will be what? This will be P plus del P del Z into dz by 2. Similarly, pressure here, this pressure will be P minus del P del Z. That means with respect to a pressure P defined at the center of the parallelepiped, we can specify the pressure at each faces. That means 2x faces, 2 y faces. X faces means faces perpendicular to x direction. 2 y faces, faces perpendicular to y direction, and 2 z faces. So 6 faces the pressures are specified like this. Now simply we find out the force balance equation. Now in x direction, what is the force balance? X direction. The force balance is the net force acting in the positive x direction must equal to the mass times the acceleration in positive x direction. Obviously by Newton's second law of motion. That means net force acting in the x direction will be the force, that means this pressure into this area minus pressure into this area. So that will be P minus del P del x, very simple, dx by 2 into the area, that is area of the x plane, AFHD is dy dz, minus the force exerted in this direction due to the pressure in CGEB plane, that is P plus del P del x into dx by 2. Area is same because it is parallelepiped, the area is same for 2x plane, and that must be equal to rho into dx dy dz times ax. So therefore we see from this equation del P del x is equal to minus rho x. So this is one very important equation. Similarly, if we make the y direction if we make the y direction balance, force balance, so it will be P similar way minus del P del y dy by 2 into what is y direction area? Dx dz. That means this is the force on the plane ABCD. Pressure is P minus del P del y dy by 2 times dx dz minus the force acting on the GHEF plane due to this pressure, which is P plus del P del y dy by 2. In a similar fashion, P plus del P del y dy by 2, and the area is same dx dz, very simple, is equal to rho times dx dy dz, that is the mass of the elemental volume, times the acceleration, uniform acceleration in y direction. So this gives rise to the equation del P del y is equal to minus rho ay. If you solve this, you will get. So in x and y direction, we get del P del x minus rho x, and y direction del P del y minus rho ay. Now what is in z direction? Now in z direction, if you see, okay, z direction, here we can write, some space is there. Here we can write for z direction. Okay, z direction, what is the net force acting on this volume in the positive z direction, please? P, so minus del P del Z into dz by 2, okay, dx dy, well, minus force due to this pressure on this surface, this is the force due to this pressure on FEB surface, minus the force due to the pressure on DAGC surface, that is P, okay, plus del P. Any difficulty, you please tell me, dz by 2 into dx dy, all right, dx dy, you can see that dx dy. Then another force, what is that one? Weight, that is acting downwards. So minus rho dx dy dz times the g is equal to again rho dx dy dz times az. That means this is the acceleration, uniform acceleration of the body in the positive direction of z axis. It is given upward. So if you solve this one, if you solve this one, you get, if you solve this one, what you get? You get, well, you get, if you solve this one, if you solve this one, you get del P del Z is equal to minus rho dx dy dz. Yes, rho g is equal to minus rho g, sorry, is equal to minus rho into g plus az. Minus del P del Z, this is minus del P del Z. If I take there, then it comes here minus rho into g plus az. From here this is clear? Okay. Now therefore we can write that in this case what we get in a fluid body, which is very important, x, y and z. That means if a fluid mass is uniformly accelerating in both x, y, z with an acceleration component ax, ay and az, then the pressure distribution in the fluid mass in x, y, z direction now follows this equation. If you recall what just we have derived, del P del y is minus rho ay and del P del z is minus rho into g plus az. Now if you see this equation and compare with the hydrostatic case, now you see in hydrostatic condition del P del x was 0. That means there was no pressure distribution in x, and similarly y direction in y if z direction is vertical. That means if ax is 0, hydrostatic condition, ay is 0 and az is 0 if there is no acceleration, or in case it moves with the uniform velocity, then also ax, ay, az 0. So whether a fluid moves with uniform velocity or doesn't move at all, there is no variation of pressure in any of the horizontal direction, but only it varies in the z direction, which becomes equal to minus rho g. Physically it means that it supports the weight of the fluid. The pressure difference created in the z direction supports the weight of a fluid element. But when it moves with an acceleration x, definitely the pressure will vary. For example, if we consider a fluid element like this, so pressure should essentially vary in the x direction, which should take care for its force acting on the body to cause an acceleration ax. So this physically implies this thing. So pressure should essentially vary in the y direction, so that the net pressure force in y direction should take care of the acceleration in the y direction. Similarly for z direction, the pressure should essentially vary to take care of the weight of the fluid plus the acceleration. So simply these are the equations obtained. Now in most practical cases, what happens is that if we have a tank, now you see this practical case, if there is a free surface like this initially, if this tank is now accelerated, for example, let us consider the acceleration in this ax direction. Now what happens, you will see the constant pressure lines will be like this, it changes like this. This is the constant pressure lines. So to solve this type of equation, let us derive in general, in this case, what should be the equations or planes, equations of the planes for constant pressure. Let us consider this for a two-dimensional first, for simplicity. Let us consider a two-dimensional problem, that means x and z. Let us consider a two-dimensional problem, that means in x and z. If we see a two-dimensional problem with ax0, az0, so we see del p del z is minus rho g. So in this case of two-dimensional problem, we can solve this with, well, we can solve this like this, that in a two-dimensional problem of this nature, let us write dp is equal to del p del x. Let us for simplicity take a two-dimensional case, del p del z dz. That means p is a function of xz. Then along a constant pressure line, we are going to search for a constant pressure line in the xz plane. If a two-dimensional case, ax is 0, az is 0, z is the vertical direction, so constant pressure lines will be horizontal. That we know. Now here let us find out in general, in case when there is an acceleration, what is del p del x is minus rho ax dx. What is del p del z? Del p del z is minus rho, as we have seen already, az dz. Alright, so we can integrate it to get the value of pressure at any point in terms of x and z. But our first idea is to find out the equation of constant pressure line. Along the constant pressure line, dp will be 0. So therefore we can write dz dx is equal to minus rho cancels ax by g plus az. That means therefore we can draw lines whose slope is like this. That means these are the constant pressure lines. That means in a practical problem of tank, the constant pressure lines will be like that. That means if there is a free surface, the free surface will be like that. So this is the slope with this. So this is theta. So that tan theta is equal to minus ax by g plus az. Now when ax is 0, that means there is no acceleration in this direction. Even if there is an acceleration in z direction, so the constant pressure lines will be horizontal, because there is no pressure variation in the x direction, because del p del x is rho ax, del p del x is minus rho x. So ax is 0, there is no pressure variation. That means it is simply giving the horizontal line, try to understand as the constant pressure line, but the del p del z will be given by rho g plus az. That means as if g is increased by an amount g plus az, when az is the acceleration in the vertical direction. But if there is no acceleration in the vertical direction, az is 0, only in the horizontal direction, then tan theta is equal to minus ax by g. In that case, az is 0. That means rho ax dx minus rho g dz is equal to dp. So therefore, if a tank is accelerated, for example, in this direction, in one of the horizontal direction, the initial free surface which is horizontal will now take a shape like this. So this will be the constant pressure lines. So the free surface will be P is equal to P atmosphere. So you have understood this? Now with this understanding, some very important conclusions will come. That when Ax is 0, the surface is, now again, if this Ax is 0, when Ax is 0, there is a Az in that direction, then the liquid free surface will remain horizontal as it is. But the pressure distribution will change, because dP is minus rho g plus Az dz. Alright, that means if we integrate it, P is equal to minus rho Ax x minus rho, these are constant, g and Az, z plus c, some constant, arbitrary constant. So when Ax is 0, this is 0, so P is simply given by minus rho g plus Az, z plus c. That means if we consider a free surface from any datum plane, if we, or exact, we could take this as the axis, Ox, Oz. So if this be Z0, and if another point we take Z, by applying this here, if it is P atmospheric, a simple application of this equation, without Ax we can write P at any point minus P atmospheric is simply rho into G plus Az into Z0 minus J. Because we will put Z is equal to Z0 where P is equal to P atmospheric. Defining Z0 is this coordinate, taking this as axis. So C will be found out. P atmospheric plus rho into G plus Az into Z0. Then we will put that value of C and find out the value of pressure P at any other coordinate Z we will get. That means if this be the depth H, that means from the free surface we know the pressure is more than the atmospheric pressure by rho GH in case of a static fluid or fluid moving with uniform velocity. But in case of a fluid moving with uniform acceleration in Z direction, so contribution of Z direction acceleration is to change the G. That means it is increasing G by G plus Az and take care of that. Alright. If there is no acceleration in X direction, there is no variation of pressure in the X direction. So lines will be horizontal. But if there is an Ax, then the lines will not be horizontal because the pressure at these 2 points will be varying as we have told. Then the constant pressure line is like that. That means in that case at two same horizontal points the pressure will be changing. Pressure will be changing because this is the free surface then. So here pressure is equivalent to this depth and here pressure is equivalent to this depth. Whether it is depth into rho G or rho G plus Az depends upon the Az. But this will be more than this. So therefore two horizontal points are not in the same pressure because there will be another constant pressure line to this point which is higher than this. So this two difference in pressure represents a net force in the X direction that has to be to balance the inertia force or the force required to cause the acceleration Ax. So therefore this thing should be very clear from physical sense and mathematical sense. This is the constant pressure line. Now another interesting result comes out if Az is minus G. That means if the tank, forget about Ax is 0, if a tank is accelerated downwards with a acceleration equal to acceleration due to gravity. That means if the tank is allowed to fall freely, the free fall of the tank, in that case we can set Az is equal to minus G according to our mathematical nomenclature. In that case del P del Z, I will not write here, from the differential equation itself del P del Z is equal to 0. Del P del Z is equal to 0 from the basic differential equation. Az is minus D. That means from this equation you can put that Az is minus D. That means P minus P atmospheric is 0 for any value of J. That means in that case the pressure at each and every point remains same. Similarly, if there is no acceleration Ax in this direction, then del P del X is also 0 minus rho Ax. That means pressure also doesn't change in that direction. That means if there is a free surface and an open tank, and if you allow the tank to fall freely, the pressure throughout the liquid body is atmospheric pressure. Pressure neither changes along this, pressure neither changes along J. So pressure neither changes along Z comes simply from the equation that del P del Z is minus rho G plus Az. You know Az minus D automatically 0. Physical explanation is very simple, that the mass or weight of the body, to balance it, the pressure differential is not required because the weight of the body causing its free fall. A body falls freely because of its weight. That means the force by which the gravitation is the force of gravitation or the force by which attracts the body. That means it is because of its weight this is falling freely. So if the fluid body is allowed to fall freely, the pressure differential in Z direction ceases to exist. That means there is no pressure differential. So pressure is uniform along the Z direction, that is del P del Z is 0. This is most important fact. You can experience it in your house or hall. One of our colleague experienced that if you have a tank, that is written in my book, and there is a hole made, and you carefully fill up the tank with this hole closed by your finger, then you let the tank fall freely. If it falls freely, you just let it down, go down from the roof of your house, you will see the water will not leak. V is 0. Why water will not leak? Because here is the atmospheric pressure. So water usual case leaks when is a static condition or any other acceleration, when the pressure here will be more than, the pressure here is P. If it is more than P atmosphere, then only water will leak. So if you fill up a container and make a hole at the bottom, the water will come out like anything because the pressure here is rho GH plus the P atmosphere, if P atmosphere is pressure. But when it falls freely, the pressure throughout is atmospheric pressure, because there is no pressure gradient. If their pressure is P atmosphere, so here also P atmosphere. So water will not leak from the hole. So this is a very practical application of it. All right? Simple? Okay, now let us solve a problem. It is very simple. Let us solve a problem. Example 1. Determine the equation of free surface. This problem is of course an worked out example in my book, but still I have given some extension to this problem. The first part is work out, which is a straightforward application of the equation that we have derived just now. Determine the equation of free surface of water in a tank moving with a constant acceleration of 0.5 g along the x-axis as shown in figure. I will show the figure, you write. That means a tank is moving with a constant acceleration of 0.5 g along the x-axis, and water is contained in the tank. The first part is that determine the equation of free surface of water. Next part is that to determine the equation of free surface, you don't require any other data. Next part, if the tank is 4 meter long in x direction, that means in the horizontal direction, 2.5 meter, that I will show. The x direction means the direction in which it is being accelerated. 2.5 meter wide, that means in a perpendicular direction, and contains water up to an initial depth of 2 meter. Contains water up to an initial depth of 2 meter. Find the hydrostatic forces on each faces of the tank. All right? Please. Please. If the tank is 4 meter long, that means I should do it. 2.5 meter wide and contains water up to an initial depth of 2 meter. Find the hydrostatic forces on each faces of the tank. Well, okay. So this problem, if you solve, the problem tells like this. Okay, let me draw the problem. This is the problem. That means initial depth is 2 meter. That means this is 2 meter, which is not required for the first part, but still. This is x direction. Let us consider this is x direction. That means in this direction, it is accelerated x. 4 meter and 2.5 meter wide, which is perpendicular to this plane. Now initially, first part is that it is given ax is equal to 0.5 g. Well, so we know the surface will be like this, constant pressure surface. We just draw it qualitatively without knowing anything, but better let us write the equation. Del P del x is minus rho ax. Del P del y is minus rho ay. And what is del P del z? Del P del z is equal to minus rho g plus az. Well, g plus az. So here there is no ay 0, there is no one dimensional, that means acceleration in this direction. So del P del x is minus, no, sorry, az is 0. So del P del z is rho g. So del P del x is minus rho x. So here del P del x is minus rho x, and del P del z as usual, even if there is no acceleration, it is a minus sign. But we can straightforward use that dz dx, that means dp is del P del x dx into del P del z dz, as I have done earlier. Just you can see that I have done earlier. Just here you see that dp is del P del z, this one. So where I have written is dz dx is minus ax by g plus h. That means I can use this formula straightforward, dz dx. That means I can again deduce this formula from here. In general, az, you can make az 0 for the specific problem. That means for the specific problem it is minus ax by g. So it is very simple. So in this case it is minus ax by g. That means it is nothing but minus del P del x by del P del z. That is del P del x by del P del z. You can derive it. You should not write a formula directly, because this will give you del z del x or dz dx. That is minus ax by g. So therefore dz dx is equal to minus 0.5 g. That means equal to minus 0.5. So if I define this as theta, this, then tan theta is equal to minus 0.5, and this gives a value of theta. Better I write the value 153.45 degree. I have solved it. That means this angle is 26.56 degree, which will be required. 26.56 degree. So this is the value. So now equation of a, this will be required afterwards. Now we cannot use this. Now better we find out the equation of free surface. You integrate this. Z is equal to 0.5x. If you integrate this, the value of tan theta will come afterwards, 0.5x plus c. So this is the equation of the free surface. That means the equation of this line which makes a slope tan theta minus 0.5. These are the equations of the free surfaces with c as the parameters. Now tactfully one can find out c and can make it 0 if we take this surface of intersection, if we take at the middle for symmetry, if we take x here and z here, then we can define that at x is equal to 0, z is equal to 0. If we take here the axis, so that c is 0. So z plus 0.5x is equal to 0 is the equation of the free surface. Z plus 0.5x is equal to 0. So along the free surface always z plus 0.5x is equal to 0, or you can write z plus 0.5x is equal to c. So the value of c depends upon a arbitrary reference for choice of the coordinate axis. This part is all right. This part is all right. Now next part, well, I can draw the figure again for the next part. For the next part, let us consider, this is again, for next part, let us consider this again, 2 meter, and this is 4 meter. Now the free surface we have already determined like this. So water is carried like this. This is now the water. This is the earlier free surface. This was the free surface earlier. So this was the earlier free surface. So now the free surface has taken a shape like this, where this is the liquid. This angle, as I have already found out, theta is equal to 26.65 degree. Now we have to find out the forces on each plane. So now tell me first, what should be the force on the vertical, horizontal plane, bottom plane? Bottom plane is the, very good. So weight of the liquid. So whichever way it is accelerated in the horizontal direction, x, it doesn't matter, the total weight of the liquid will be the force here. But if it could have been accelerated in the z direction, then the force will be weight plus the acceleration. That means as if we will consider g is increased by g plus az or minus az, downward. If there is a free fall, what is the force on the bottom? 0. You must know this thing very carefully. So now the bottom plane, the weight is simply, we equate the weight, that means rho. That means rho is 10 to the power 3 into v. V is 4 into 2.5 into 2. This is the total volume. Initial depth was 2. So v into rho into 9.8. I have taken care of all these things. V into rho into 9.8. 4 into 2 into 2.5, 9.8 Newton. So this becomes is equal to 196 kilonewton. This is as simple as anything. Now what are the forces on these two planes? First of all, consider leading plane, leading phase. What is leading phase? This phase. That means phase, leading means the acceleration is taking place, the leading phase. What will be the component forces? If you see this phase in this direction, this is a phase like this, where this dimension is 2.5 meter. Okay, I see from this direction, this is the phase. So this is the free surface. So free surface is this. So this height, let this height is, what is this height? This is not 2 because water touches. So free surface is parallel here because there is no acceleration in this direction. So free surface is horizontal here from this point. This is not 2. So this value is what? This value, let this is H1. This H1 is what? H1 is, I write H1. What is H1? 2 minus 4, 2 into tan of 26.6. 2 is the half of this. That means this minus this. What is this value? This value is 1 because it is 0.5. Correct. So you see, if the problem is said like that, students will not be having any difficulty. So therefore, this is the force on a vertical surface which is submerged up to a depth of 1 meter. H1 is 1 meter and this width is 2.5 meters. So therefore, it is rho G into the pressure at the centroid or center of area into 0.5 into 2.5 into 1 Newton. So this becomes also very simple calculation, 12.25 kilonewton. Similarly, for this trailing phase, please tell trailing phase. Trailing phase is the same thing, only difference is the 3. Very good. Now this is 3 meter, H2. H2 is equal to 3 meter because 2 plus this quantity, 2 plus tan 26.25 degree, which is 0.5, that is 2 into 0.51. So 2 plus 1. Very good. So this remains as it is, the width perpendicular direction 2.5 meter. So what is this value? 10 to the power 3, 9.8 into 1 into 2.5 into 2. Okay. 1.5 because 3 ka center is 1.5, rho G 1.5 into 3 into 2.5 area. I am sorry. So don't do that mistake. I may be escaped as a teacher, but you in the examination. So 1.5 is the center of area. So 2.5 into 3. So after that, if you do a mistake, the reduction of mark will be less because your concept is clear. Because some silly mistake, your concentration was not there, you have calculated wrong. But here if you write 1, the way I have written, then I will think that okay, you have not understood. Center of area is middle of that. That should be 1.5 and area is 2.5 into 3. So then you can do the mistake in calculations, you can afford to do, but you should not. Probably I have got the result 110 point. So now remaining other 2 lateral faces are there where the forces will be identical. That means a vertical face like this where the free surface of water is adhering like that. This is the water. So how to find this? By integrating. Very good. So simple by integration. Very good. By simply integrating. I can use another pen. Well, good. By simple integration. That means you can take a strip like that. For this purpose, I define this as the x-axis and this axis, z-axis. So therefore, for this strip, the force dF is what? If this is z, this coordinate of the free surface with respect to this x-axis is z. That means this is z. So center of area is z by 2. So rho g z by 2. And its area is, if we define this thickness as dx, because this is the x direction, it is very simple, z into dx. So simply f for the entire surface will be df is equal to integration rho g I take outside, incompressible, that is a liquid, and z square by 2 dx. 2 also I could have taken outside. Okay, though this should be h2 minus h1. From this I am going the positive direction. And another constant is that dz dx is equal to, what is dz dx? Minus tan theta. Here if I define this as the theta, Now again this has the theta, so tan theta. So simply dz dx. No question of pressure, it is geometry, because dx is increasing and dz is decreasing. With increasing z, z is increasing x, z is falling. So dx by dz is equal to minus tan theta. That means if I now substitute it, it should be F is equal to rho g by 2. That means we can take h1, h2, change the dx is dz by tan theta. That means you take tan theta out, dx is dz by tan theta. That means z square dz. That means simple rho g z cube 6, 3 into 2, 6 tan theta into h1 cube. ठीक है? h1 h2 we know, sorry, h2 cube and h1 cube. h2 has gone up because of this minus. This tan theta is tan of 26.65 from geometry. We have taken this theta. Okay, this thing is okay. This is the force acting on each of the lateral faces. That means front face and there is another back face. Any problem? Okay. This is the equation. Please. No problem. So, with full confidence on you, I can leave you today for this midterm examination. So, this is up to this. In next class, I will discuss few other problems of this section and I will start the next section of this course. Applications of conservation equations in fluid flow problems in practice. So, okay, thank you. Good morning. I welcome you all to this session of fluid mechanics. Today we will start a new chapter, a new section, that is fluid flow applications. We have already discussed the conservation equations, that is the conservation of mass, equations for conservation of mass, conservation of momentum and conservation of energy, and we have solved some problems related to finite control volumes, both inertial and non-inertial control volumes. Now, in this section, chapter, we will discuss few practical problems of fluid flow applications, which will be solved on the basis of the equations for conservation of mass, momentum and energy, the applications of those equations. Better we can say that it is the application of conservation equations to fluid flow problems. At the outset, we will discuss little bit about the Bernoulli's equation or Bernoulli's theorem, which we have discussed earlier, a little elaboration on that. If we recall, we earlier recognized the Bernoulli's equation as the equation of mechanical energy or mechanical energy equation in case of a fluid flow, which tells about the conservation of energy in a fluid flow. And we have recognized that if the fluid is inviscid, obviously the mechanical energy remains constant. If there is no energy added from outside, no mechanical energy is taken out of the fluid, and if the fluid is inviscid, that means viscous action is not present, that fluid is inviscid, no viscosity, that means no friction. So mechanical energy cannot be dissipated in terms of intermolecular energy or heat, as you can tell. So in that case, total mechanical energy remains constant. And we have seen that in general, this mechanical energy, total mechanical energy remains constant along a streamline. And we have recognized different forms of mechanical energy as the pressure energy, kinetic energy and the potential energy. If you recall the equation, you can tell that P by rho, which represents the pressure energy per unit mass, plus V square by 2, which represents the kinetic energy per unit mass, we have to always recall in this form, plus Gz, where Gz represents the potential energy per unit mass. Here of course we consider only the Earth's gravitational force field as the only body force field. So therefore the potential energy per unit mass will be Gz, where G is the acceleration due to gravity and Z is the elevation of the point concerned, where we are considering the energy per unit mass from an arbitrary datum. So P by rho plus V square by 2 plus Gz thus constitutes the total mechanical energy, and which is equal to constant for an incompressible steady flow, because this form of the equation comes only for a steady incompressible flow. That is of course important, otherwise integral dP by rho will come for a compressible flow, but P by rho, this term comes for an incompressible flow. So for an incompressible steady flow, P by rho plus V square by 2 plus Gz, simply the sum of the three components of the mechanical energy is constant along a streamline. If you recall the derivation of this equation, we did it by integrating the Euler's equation along a streamline. Probably you can recall this, that integrating the Euler's equation along a streamline. So therefore the constant which came out of this integration was a constant, that means it was valid only along a streamline. So therefore essentially the mechanical energy varies from streamline to streamline in general. But now we will extend this in case of an irrotational flow. That means if we add a further constraint in the flow, that if the flow is irrotational, already you have studied what is an irrotational flow in fluid kinematics, that a flow is irrotational when the rotation at each and every point is 0. And you know the rotation of a fluid element at each point is defined as the curl of the velocity vector, curl V. In different coordinate system we can expand this curl V. Physically the rotation means the arithmetic average of the angular velocity of the two linear segments meeting at that point, which was initially perpendicular. So rotation is 0 means the flow is irrotational. So if we add a separate or additional constant of irrotationality, that means the flow becomes irrotational, inviscid, steady, incompressible, then this mechanical energy is constant throughout the flow field. That means P by rho plus V square by 2G plus Gz is equal to constant not only along a streamline, but at any point in the entire flow field. This we will derive first, which is a very simple derivation. Let us do it. Let us see this. Let us first take a two-dimensional case, a two-dimensional flow. A two-dimensional flow in a Cartesian coordinate system. In a Cartesian coordinate system, in a Cartesian rectangular, that is Cartesian coordinate, a Cartesian coordinate system. And in this case, let us consider only x and y, no z, so y we consider, and this we consider the y-axis is in the vertical direction, y directed positive upwards, vertically upwards, so that g is acting like this. So if this we consider as the frame of coordinate, and also we consider a steady and incompressible flow. If we consider a steady and incompressible flow, steady and incompressible flow, then if we recall the equation of motion, that is the Euler's equation, we can write that for a steady the temporal derivative will not come, u del u del x plus v del u del y is equal to minus 1 upon rho del p del x, if you recall. So this is du dt, big du dt, big du dt. That means this is equal to minus 1 upon rho del p del x. This is the x direction. So this has been expanded. Del u del t is 0 for steady state, so I have not written. Del u del t is 0 for steady state, and rho is minus 1 upon rho del. This is the form x direction equation. Y direction equation similarly will be dv dt, if you recall, is equal to minus 1 upon rho del p del y. So if you expand this in case of steady flow, that means del v del t 0, then you get u del v del x plus v del v del y is equal to minus 1 upon rho del p del y. So these two equations are the equations for incompressible steady flow with respect to a two-dimensional Cartesian coordinate system. Of course, here I am wrong. Minus rho del p del y, here g is here acting. So we have considered the y-axis such a way that vertically upwards directing positive. So g is in the negative direction. So body force term will come
which will be here minus g, because these are the force per unit mass, because here this left hand term is the acceleration per unit mass. So first term on the right hand side is the pressure force per unit mass. So per unit mass the body force will be minus g. Why minus? Per unit mass it will be g, mg divided by mg, and it is in the negative direction of the positive y axis. So therefore minus g, this comes as the body force. If you recall the body force, here the body force is 0, in the direction of x there is no body force. So we have chosen the y axis in such a way that it is directed upwards, vertically upwards, so that the gravity force comes as the body force. So per unit mass basis it appears as minus g. I am sorry, so this term will. Now what we will do, we simply know that the basic approach for finding out the energy equation is to multiply the momentum equation with the displacement. So what we do, if we multiply this equation, x direction equation by dx, and multiply the y direction equation by dy, both these sides, and add it, what we get, u del x dx, we first take the u term common, then from this equation it will be del u del x dx, and from this equation it will be u del v del x dx. Okay. U del v del x dy, sorry, u del x dx plus v del v del u del v del x dy plus v del u del y dx plus